Getting your Mecanum robot to glide effortlessly in any direction, sideways, diagonally, forward, backward, it's a pretty common goal. And frankly, it's often a sticking point for many builders, but it doesn't have to be. In this video, I'm going to show you exactly how to program a Mecanum drivetrain using Python, allowing you to get that precise omnidirectional movement. This is a key skill if you want to truly build agile robots. I'm Brogan Pratt, and with over 10 years of robotics design and a technology educator, I've guided countless students through this very process. I'll quickly go over my specific robotic setup, then we'll dive right into that Python code, step by step, so that by the end, you'll have a robot that drives exactly where you tell it to. Let's go get started. So taking a look at our test chassis we're going to be using for this, and these are the assumptions that I'm making in terms of programming. I'm using the Mecanum Strafer chassis from GoBuilda. It has ×4 DC motors down in it. Any DC motors work for this. I'm using 312 RPM motors from GoBuilda. And then for the electronics, I'm going to be programming using a Metro Express board. You could use a Metro M4 Express. Attached to this Metro M4 Express, I have a FlySky FSI6 controller. That's this guy here. This is what I'm going to be using to be able to control this device. Obviously, we're going to have forward and backwards, strafing left and right, and we're going to use this for rotation. If you want a video about how to program this, I've got that down in the description down below. As far as the wiring goes up, I have two RoboClaw 2x30 amp controllers here. These are wired up in serial connection. These are wired up in serial connection via tank drive. That is mode 1, option 4. And I have two DC motors connected to each one specifically. You have a common ground coming back, and then you have, on your first two servo ports, these control each motor individually, sending PWM signals over via your Metro M4 board. So looking at our board here, we have front left, front right, rear left, and rear right. And it's got two battery packs. One is powering DC motors, one is powering the Metro 4 Express board. And then on this RC controller, I'm going to be reading channel 1, channel 2, and channel 4. So let's go ahead and start actually programming this up. So over at our coding program, let's take a look at how we're going to break down our steps for today. So our programming steps today are, 1, we're going to have to set up our RC controller so we can have our inputs. 2, we're going to set up our DC motor controllers. We're going to have to set up, or we're going to have to create a helper function that converts milliseconds to a duty cycle pulses. We need to do that because our motor controller assumes you have a 400 milliseconds of range, but we need to convert those into duty cycle pulses because that's actually how we're going to control our motors. After that, we need to create a helper function that normalizes the joystick input. And then finally, we're going to create a drive function that takes our normalized inputs and outputs Mecanum to drive motor commands. So let's start with that first part where we need to actually set up our RC controller. First thing we do, as usual, is we're going to import time. We're going to import board. And we're also going to say from RC, import RC. So this is a class you can find in the library down below that allows us to use the FlySky FS1 or i6 controller with CircuitPython or Python. And we're going to create the RC object. And this was simply going to be RC equals RC. And then here's where we create all of our different channels. So we're going to be reading channel 1, and this is going to be board.D9 in my case. So actually, sorry, this is D10 in my case. Channel 2 is equal to board.D11. Channel 3 is equal to none because we're not reading channel 3. And channel 4 is equal to board.D9 in my case. Channel 5 is equal to none. And channel 6 is equal to none as well. Oops, not equals. So that is our RC object initialized. If you'd like to have more switches, you could go ahead and actually import these channels. But so in this case, we're not actually going to be doing that. Then let's actually read our channels, and this is pretty easy. So we'll say while true, we're going to say our throttle is equal to rc.read_channel, and our throttle is the y-axis on our right joystick, which is channel 1. Our strafe is equal to rc.read_channel, and our strafe is actually going to be channel 2. Then finally is our rotate, and that is equal to rc.read_channel, and this is going to be channel 4. Now at the very end of our loop, because we're reading on that RC, on the specific controller we're using, we are reading PWM cycles, and we need to stay within a PWM loop. So I'm actually going to put in a time.sleep for 0.02, and this keeps us in cycle with the PWM of the RC controller. We've now set up our RC controller. We're ready to rock. Let's go on to the second step, which is setting up our DC motors. Now for our DC motors, we need to import another library. We're going to import PWM IO, or pulse width modulation in out. And let's actually create these 4 different objects. So we're going to create 4 motors. We're going to say motor underscore front left is equal to PWM IO dot PWM out. And this one is going to be, our front left is board.D0, and it's got a frequency of 50. We're going to create this for our front right, our rear left, and our rear right. And thankfully, using Copilot, it's actually pretty smart here. These are all actually correct. So we've got our front left, front right, rear left, and rear right, all to our respective motors. Now, before we continue on, we need to set up some default ranges so we know where we are actually at. Using the robocall controller over serial output, the stop milliseconds is equal to a 1.5 millisecond pulse. So if you send a 1.5 millisecond pulse to a motor, it's going to stop it. Our max milliseconds speed is going to be 1.9, and our min millisecond speed is equal to 1.1. So we actually have a 400 millisecond range, plus or minus, to control max power of the motors. You might want to check the documentation on your motor controller to make sure yours is the same, but for my motors, this is where things are going to be sitting at. So now we've got our default set up, it's time to go ahead and convert those millisecond pulse commands into a duty cycle. We're going to use a helper function to do this because the duty cycle is going to be a full 16-bit analog range, which means we've got 65,535 values to work through, which is why we're using these millisecond cycles as opposed to having to type it in. So we're going to create a new function, and we're going to say millisecond to duty cycle. And for this, we're just going to assume a frequency of 50 because we've already done so. So we're going to say it's going to take millisecond as an argument. It's also going to take frequency as 50. First thing I'm going to do is I'm going to take a period of milliseconds is going to be equal to 1.0 divided by our frequency multiplied by 1,000. And then to actually get our duty cycle is equal to an integer division of our milliseconds divided by our period milliseconds divided by 65,535.0. So that gets us our duty cycle number. Now we need to make sure that the duty cycle that we send is in between the ranges of 0 and 65,535. So the last thing we're going to do is we're going to do a quick clamping helper function. So we are going to return the minimum of 65,535 and the maximum of 0 and our duty cycle. So this just clamps the duty cycle from 0 to 65,535. Effectively, how it does that is first it's going to calculate the maximum value between 0 and the duty cycle. It's possible that our duty cycle gets calculated as a negative number, in which case the maximum we should take is a 0. And then it's going to take the minimum number between the absolute maximum value and whatever the value was here. So it's possible that this duty cycle ended up being 70,000. Then it's going to take that minimum number between those two. So it'll always pull between 0 and 65,535. So next is one of our really important helper functions. We're just going to create a stop all function. It's really useful in robotics to have something you can use as sort of your red button if something goes wrong. So let's create that. So we're just going to find stop all motors. It's not going to take anything. And whenever we call this, we're just going to stop everything. So I'm going to say motor underscore front left dot duty cycle is equal to our milliseconds to duty cycle function and then stop milliseconds. We're going to call that down for all of our motors, for our front left, our front right, our rear left, and our rear right. So whenever we call that stop all motors, it's going to send that millisecond to duty cycle helper function with our stop milliseconds, which of course is 1.5. So this should stop all of our motors. Important thing about this roboclock controller is whenever you send a command to it, the motors will continue to run. So if you don't send a stop command, they won't actually stop. So this is a really useful function. At this point, we've set up our RC controller, we set up our DC motor controllers, and created the helper function that helps us convert those milliseconds over that duty cycle. Next, let's go ahead and create that helper function that normalizes that joystick input. The reason we have to do this is with the RC controller that I'm using, it expects a range of 0 to 100 from the joystick. However, in order to control Mecanum wheels, Mecanum kinematics expects between negative 1.0 all the way up to 1.0. So we need to be able to normalize that input value from 0 all the way up, or from negative 1 all the way up to 1. So let's go ahead and create that function. So I'm going to say define normalize input, and we're going to take a value as our parameter. Now the first thing we need to do is we need to set up our dead zone. And what a dead zone is you'll probably find that with some controllers, that center joystick doesn't really bring itself back all the way to center. We would expect that 50 is the center, but sometimes when it releases back, it's not always back to that center. So we're actually going to say dead zone min is going to be equal to 45, and the dead zone max is going to be equal to 55. And then we'll check if our value is within those dead zone mins. Before that, we're actually going to check if the value is equal to none. We're simply going to return 0. So if our value is equal to none, we're going to return 0. What this does is if we pass in a none value, and that will get exported, or that will get returned with that RC controller, it returns none if it gets an invalid reading. So this allows us just to stop the controller. The 0.0 is going to end up actually creating a stop for us because that's our mid value. Then we're going to check if our value is inside that dead zone. So we're going to say if the dead zone min is less than or equal to our value, and our value is less than or equal to our dead zone max, so our value is in between our dead zone, we're actually going to go ahead and return 0 again. So a lot of stopping functions, but again, robots are all about safety. So now that we know that our value is going to be in that dead zone, let's actually see what happens if we are pulling back on that controller or below our dead zone value. So we're going to say elif the value is less than the dead zone's minimum value. We're going to return our value minus our dead zone min divided by our dead zone min. So effectively what this is going to do is it's going to turn whatever that value between 0 and 44 is into a decimal number between negative 1.0 and 0.0. Then we're going to say elif our value is greater than our dead zone max. We're going to return our value minus our dead zone max divided by, this time it's going to be 100 minus our dead zone max. And this is going to do the exact same thing. It's simply going to return above 55, and it's going to convert that 1.0. So at this point, we've now got all of our helper functions set up, and now we can actually finally go ahead and create that drive function that's going to go ahead and move our Mecanum wheels. So we're going to go ahead and say define drive. And our drive is going to take 3 parameters. We need to take our throttle speed, we need to take our strafe speed, and we need to take our rotate speed. And so we're actually going to one more. We're also going to add in an input scale. And what an input scale does is it allows us to effectively change the sensitivity of those joysticks. So if you find, rather than having to change the joysticks themselves, you can change the 0.5. If you make it greater up to 1.0, it'll make it so you get an absolute transfer. If you bring it down, it makes it so that your joystick command doesn't go as fast. It'll make things a little bit less jumpy. It's nice to have a bit of proportional control in here. This is future Brogan coming in to edit this. I realized I made a mistake there. it should be strafe. And now my whole function will actually work. I had accidentally wrote this as input scale in parentheses 0.5. It should actually input scale equals 0.5. Didn't catch that until I went through back and edited it. So the first thing we're going to do is we're going to normalize all those inputs. So we're going to normalize our forward input, which is going to be our throttle speed, but we're going to put it inside our normalized input value. So we're going to say normalize input, and we're going to normalize our throttle speed input. We'll do the same thing for our strafe and our rotation. So I'm going to say that strafe is equal to, again, normalized input, but our strafe speed, and then rotate is equal to that normalized input, but our rotate speed. Then we're going to check if those values that we sent are within that dead zone. So we're going to say if our forward is equal to 0 and our strafe is equal to 0 and our rotate is equal to 0, we're just going to call stop all motors and then return a null value. This is, again, another one of those safety functions. If your joystick happens to be in the direct center, you're not touching anything. When you're calling drive, of course, nothing should be moving. If those values happen to be outside of drive, let's go ahead and actually send those out. So we're going to multiply in our scale so that we can scale down some of that sensitivity. So we're going to say forward is equal to forward times input scale. Same thing for strafe and same thing for rotate. Now let's actually do our Mecanum kinematic equations here. So in order to do those equations themselves, we're going to send power to each individual motor. So we're going to say motor underscore front left power is equal to forward plus strafe plus rotate. Our motor underscore front right underscore power is equal to forward minus strafe minus rotate. And then our motor underscore rear left power is equal to forward minus strafe plus rotate. And then our motor underscore rear power is equal to forward plus strafe minus rotate. And I actually have a spelling mistake here. There we go. If you want a deeper explanation into how these kinematics actually work, I've got a video in the description down below about how these mathematics actually transfer those forces into directional movement for your Mecanum drive. But effectively, this is the quick equation that allows you to move everything out. Next, it's time for us to make sure that we clamp that power between -1 and 1.0. What you'll find is that it's entirely possible that you have a forward and a strafe value of 1 and a rotate of 0, and it's not possible to have a motor command that is greater than 1. The problem with that is you cannot send 200% power to one motor and 100% power to another because it'll only accept 100%. So we're actually going to scale everything down a little bit so that it clamps it between. And then if one of the motors is at 200%, one of the motors is at 100%, we're actually going to call the other motor at 100% and the other motor at 50% so that the ratio stays the same for what it is that we would expect the output to be. If we don't do that and we would want to go forward diagonal, we'll actually end up not moving the direction that we want. So the first thing we need to find is we need to find which motor is currently the strongest. And the current max power is equal to the maximum of our absolute value of our motor front left power, then the absolute value of our motor front right power, absolute value of motor rear left power, and rear right power. We grab that absolute value because it's possible we have a negative 2.0, so it basically removes that negative and says whatever our current value is. Then Copilot is smart enough here that if our maximum power is greater than 1 or higher than that, we're going to scale all the motors down based on whichever power was the highest. So it's entirely possible that one of them is actually sending 3.0 value. So then it would scale everything down by a third. Now, the last thing we need to do is actually command the motors to move. So we're actually going to move the motors and convert to milliseconds. So we're going to grab our motor underscore front left dot duty underscore cycle is equal to, so we're going to actually send out that duty cycle in something that is between 1.1 and 1.9. We're actually going to take our stop milliseconds value. We're going to add in that motor front left power. And we're going to multiply that by 0.4 because 0.4 is that range in between. And that's going to end up giving us that value between 1.1 and 1.9. we're going to go ahead and do the same thing for the front right, the rear left, and the rear right value. So now we've got our drive function set up. Let's actually go ahead and control these motors in the very end. Add inside of a while true loop, after we've read all the values for our controller, we're going to go ahead and simply grab drive, and we're going to call it with throttle, strafe, and rotate. And that's it. That's how we actually program something up in Mecanum Drive. Let's go take a look and see at how this actually works around. So a brief overview of how everything works again. We set up our RC controller. Again, that's for my specific setup. You might be using a Bluetooth controller, whatever it has. We set up our DC motor controllers. We create that helper function that converts our milliseconds to duty cycles, create that helper function that normalizes joystick input, then creates that drive function, actually takes those normalized inputs and outputs it into those Mecanum Drive motor commands. We import the required libraries, create our RC object, go ahead and create our DC motors. For ours, my specific commands are stop of 1.5 with a maximum minimum of 400 milliseconds either way. We have that helper function that converts our milliseconds into a 16-bit cycle. And then we also have our stop motor function. We've got our normalizing value that allows us to keep track of dead zones. If you find this dead zone is too great or too little, you want things a little more sensitive, you can change those dead zone values. This is where we actually drive. We take in our throttle speed, our strafe speed, and our rotate speed. We check if those are all 0, we stop our motors. Otherwise, we multiply up our input scale, and then we do our actual Mecanum mechanics before we check. And if anything's greater than 1, we ratio everything down before finally actually sending those motors out. So I hope you found that a useful case in converting Mecanum Drive into Python controllers. If you got any questions, let me know in the comments below. And if you have ideas for future projects or other things you need help with, shoot a comment and maybe I'll make a video on it in the future. So I hope you had some fun and best of luck with your next robotics project.